We just studied the 2 subdivision formula for trapezoid approximation. Let's take that to 3 and generalize it to k. For 3 subdivisions, we will apply the trapezoid approximation to exactly 3 subdivisions of the interval a to b. There they are as shown. H is b minus a divided by 3, that overall width split into thirds. The 3-division approximation is just the sum of the areas of the individual trapezoids. There they are. That's the area of trapezoid 1, and then the area of trapezoid 2, and then the area of trapezoid 3. Again, notice that the function values at a plus h and a plus 2h both appear in 2 of the formulas, hence their overall contribution is twice. Here it is f of a plus f of b plus 2 times f of a plus h plus 2 times f of a plus 2h. Let's capture that in a formula. The 3 subdivision trapezoid formula involves h over 2, f of a, 2 f of a plus h, 2 f of a plus 2h, and f of b. What about an error bound for this formula? Well, remember that the error bound in each subdivision is m2 times h cubed over 12. There's 3 subdivisions, and h is b minus a over 3. Now the integrals add, therefore a bound on the overall error that's being made is just the sum of the errors on the individual bounds. These individual error bounds are all identical, so we need 3 of them. 3 times m2 times h cubed over 12. Substituting in for h, b minus a cubed over 3 cubed, one of the 3's cancels, and we're left with m2 b minus a cubed over 12 times 3 squared. Assuming m2 is a bound on the second derivative of f over the interval, then this is an absolute bound on the error between the 3 subdivision trapezoid formula and the actual integral. Let's compare that to the original bound for the single trapezoid. The single trapezoid had an error bound of m2 times b minus a cubed over 12. That's what you get with 2 function evaluations at a and b. What about with 3 function evaluations in the 2 subdivision? Remember, in the 2 subdivision, the error bound is exactly the same bound, but it's also got a factor of 2 squared in the denominator. The error bound is a factor of 4 better. What about for 3 subdivisions, which we just did? The error bound is the original bound, but with 3 squared, or 9 in the denominator. So with each additional function evaluation, the guaranteed bound on the difference between the trapezoid approximation and the actual integral is getting smaller quite quickly. The 2 subdivision has an error bound 4 times smaller than the 1 subdivision, and the 3 subdivision has an error bound 9 times smaller than the 1 subdivision. Let's generalize this to k subdivisions. For k subdivisions, do the obvious. Apply the trapezoid approximation to k subdivisions of the interval a to b, and this requires k plus 1 function evaluations. Here I've drawn it for k subdivisions. I've just got 3, but the general formula should make sense. H is b minus a over k. That's the width of each subdivision. And the trapezoidal approximation to the integral is the sum of all those areas. When those are summed up, each of the intermediate points plays a part in 2 separate integrals, the trapezoids that it's a member of. Therefore, the value of the intermediate points counts twice with a 2, and the value of the endpoints fa and fb counts once. If we do an error estimate, well, again, the error bound in each subdivision is m2 h cubed over 12. And in this case, there are k subdivisions, and h is b minus a over k. As I've mentioned several times, the integrals add, so an error bound for the entire summation is simply a sum of all the error bounds for the individual terms. That means k of these individual error bounds, k times m2 h cubed over 12. Now make the substitution for h, b minus a over k. And what we end up with is m2 b minus a cubed over 12 times k squared. For k equal 1, this was the bound for the original trapezoid rule, 1 subdivision. For k equals 2, this was the bound for 2 subdivisions. and 3, and here it is in general for k subdivisions. Let's go into Matlab and see the effect of increasing the number of subdivisions on calculating the integral of sine of x from 0 to pi over 2. Here I am in Matlab. Let's go over what I have here. Limits of integration, 0 to pi over 2. We'll do k subdivisions. We'll vary k from 3 to 99. We'll keep track of the errors at each instance of this. So the error in the trapezoidal approximation will be a vector that we'll fill in. The true value of the integral of sine of x from 0 to pi over 2 is 1. Now let's loop through and try different values. So on the first time through, k will equal 3 subdivisions. X will be a linearly spaced vector from a to b with k plus 1 points. Remember that for k subdivisions, there's k plus 1 function evaluations. H is b minus a over k, and the function value is simply the sign of the argument. X is a vector, sine is vectorized, therefore f will be a vector of the same length, also k plus 1 points. The formula for the trapezoidal approximation is h over 2 times the first function evaluation plus the last function evaluation plus 2 times the sum of all the intermediate function evaluations. The error at this particular trial is equal to the true value minus the trapezoidal approximation, and we'll take the absolute value of that. Loop over all of these from 3 to 99. Then let's do a log-log plot, plotting the error versus the number of subdivisions. Subdivisions on the horizontal, absolute error on the vertical. Let's try that out. There it is. We notice on a log-log plot, the slope is about -2. Here, let's move across a factor of 10, and we see that we move down 2 factors of 10. So this line is completely consistent with the error bound that we proved, that the guaranteed error decreases with the square of the number of subdivisions. One last issue to discuss before we close out the composite trapezoid formula is the effect of noise or errors in the function evaluations. How does the inaccuracy in evaluating f of xi affect the value of the k subdivision trapezoid approximation to the integral of f over the interval a to b? Well, if we make some assumptions about how the error or inaccuracy arises, we can make some concrete statements. Let's suppose that the error is additive, so that the evaluated value differs from the true value by an amount mu sub I. The evaluated value of f at xi is the true value f of xi plus mu I. This is for all the points a equal x1 all the way through b equal x k plus 1. Now the trapezoidal approximation only involves summation. So when this summation is performed using the evaluated values, both the summation of the true values is carried out and the summation of the errors is carried out. Therefore, the error induced by the mu i's is just this sum of the mu i's, namely h over 2 mu 1 plus 2 times the sum of all the intermediate mu's plus the last mu. For large values of k, it's just approximately this. Now generally, if the trait of the errors are that some of them are positive and some of them are negative, kind of in a random fashion, then this sum will be quite small because there'll be lots of cancellations. So generally, the effect of random noise on integration is quite small because of the cancellation of all these random effects. We'll see a lot more about this in the statistics module, which is upcoming. For now, let's just keep that rule of thumb that random errors, plus or minus, tend to cancel out in performing an integration.